We've got Denise. Denise is coming from the University of Hawaii, and she's going to be talking about optical and infrared discovery of large-scale structure and the characterization of the cluster mass function at z = 1.
All right, thank you. Hi, everyone. Thanks for coming. Today, I'll be discussing the application of a new cluster finding technique with optical and near-infrared data at Redshift 1. Our data set is the ORELSE survey, which is a large-scale structure survey with optical and near-infrared photometry and spectroscopy. ORELSE was targeted at around 20 intermediate redshift large-scale structures across several fields, which were selected by X-ray, optical, and radio observations. Through a naive search in each field, we found a few dozen more clusters and groups, increasing the total number to just over 50. But there should be far more structures in the data we missed, and our goal in this work was finding every one of them in the data set we have. The data set we have of ORELSE dwarfs many other large-scale structure surveys in both the number and redshifts and limiting spectroscopic magnitude. The wealth of photometric and especially spectroscopic redshifts makes ORELSE a prime data set for a serendipitous cluster search. Spectroscopic redshifts have an order of magnitude greater precision and accuracy than photometric redshifts, and this work would not have been possible without the over 10,000 spectroscopic redshifts we obtained from Denis over a 15-year campaign. For our cluster search, we divide up our full redshift range into a series of redshift slices. These slices give us a 2D plane of galaxies where we can apply our density field estimator called Voronoi tessellation. In the Voronoi tessellation, you define a cell for every galaxy in the field, and the region of the cell is the area closer to the cell's galaxy than any other galaxy. The density is then the inverse of the cell sizes. Unlike other density estimators such as nearest neighbor, Voronoi tessellation is scale independent and can be used over large physical lengths. Most importantly, for finding irregularly shaped overdensities, it makes no assumptions about the geometry or morphology of structures in the field. The photometric redshifts in our data have much larger uncertainties than the spectroscopic redshifts, so we use the Monte Carlo method where we Gaussian sampled the photometric redshifts and averaged the tessellations over 100 realizations to create a final VMC overdensity map. We used the photometry package source extractor to identify significant overdense pixels in our Voronoi Monte Carlo maps. These overdense pixels are represented in source extractor as an isophotoflux, which is a measure of density. A galaxy cluster is going to span some range in redshift. So likewise, we want to link our source extractor detections in neighboring redshift slices together. For this example here, I happen to require each object to be within a distance of 0.5 megaparsecs to be linked together, but this can easily be changed. We linked objects between successive redshift slices until no more objects within range are found. We then take all linked objects and fit a Gaussian to finally obtain one overdensity candidate. Here, all the ellipses mark source extractor detections, and the white circle marks objects we're linking together. We don't directly have a mass estimate for our overdensity candidates, but we do have the dynamical masses of previously found clusters and groups in ORELSE. These masses are reliable because we have a high fraction of spectroscopy for these structures, and therefore we have complete dynamical information. For each one that we recover, we have both an integrated isophotoflux from the area of the Gaussian fit and a measured virial mass. We thus fit the isophotoflux for the mass to get a function that we can use to estimate the masses for all of our new overdensity candidates. We estimated our purity and completeness by injecting structures into mock catalogs, where we deliberately set a fixed fraction of spectroscopic redshifts, similar to the range we see in our real data. Even at low masses and low spectroscopic fractions, we see very high purity estimates and completeness of greater than 50% at a spectroscopic fraction of around 20%. Note that our mass range is limited to about 13.6 dex, because for lower masses at high redshifts, our synthetic groups would have so few Gaussian numbers bright enough to be detected that the Voronoi tessellation had issues with converging. With our cluster finding technique, we found an order of magnitude more overdensity candidates in the ORELSE fields than the previously known clusters and groups. Though we required a candidate to have a spectroscopic fraction of at least 5%, many of the candidates we found were around 20%, suggesting that even a modest number of spectroscopic redshifts can produce fruitful cluster searches. Our sample is complete down to about 13.6 dex, which is slightly better than the mass limits of cluster studies with Sloan data for the local universe. The purity and completeness corrections are important to consider when we use our overdensity candidate sample to derive a cluster mass function. Our cluster finding technique involves many independent parameters that affect the number and masses of candidates in the final output sample. Previously, we opted to adopt a set of parameters that emphasize detection of as many structure steps as possible. However, there may be cases like large structures that are composed of blended smaller overdensities. For the mass function, we need to know the number of overdensities at each mass. We do not know a priori what the correct distribution of overdensities in our data is, so we consider several input parameters, such as the detection and deblending parameters in source extractor, and we vary them over a reasonable range of values. We average the candidate samples over every input parameter we vary through a Monte Carlo method, and we get the number density function plotted here. The color bands show theoretical mass functions for a few different cosmological parameter values for reference. So we can fit for the cosmological parameters omega matter and sigma 8 by varying the values in the theoretical mass function and then measuring the chi-square offset with our observed densities. Here we plot the likelihood as a function of chi-square. The peak likelihood is our best fit pair of parameters, and we have uncertainties estimated from a 1D collapse likelihood functions. Compared to the WMAP 9 values, we see omega matter within a 1 sigma agreement, but our sigma 8 is high by about 2 sigma. This is a consequence of ORELSE being designed to target previously known massive large-scale structures over a smaller volume, which biases our number densities high. We can try to mitigate this bias by excluding the previously found structures, which make up almost all of the highest mass structures in our sample. Doing so does reduce the sigma 8 disagreement, but only by about half a sigma. However, we present this work as a proof of concept that a purely optical cluster mass function is possible at Redshift 1, which has not been done before. Our cluster finding technique can also be applied to any large photometric and spectroscopic data set, which we can expect to see more of in the near future with upcoming instruments like the Subaru Prime Focus Spectrograph and large surveys such as Euclid. Thank you for listening. I'll take any questions now.
Thank you. I don't see any questions quite yet on the Q&A or the Slack channel. One of the questions I have is you were talking recently, just at the very end here, about the samples and future telescopes. Can you expand upon how you would be following up with those?
This technique is generically applicable to any data set with a lot of photometry and spectroscopy. So if you happen to have so for example, for Euclid, you get a lot of photometric reshifts from them, and then from the Subaru PFS, you get spectroscopic reshifts. So if you can combine that data set, you can apply the same technique to a much larger field. So you could probably find a lot more overdensities and actually derive a cluster mass function that doesn't have the limitations we do here with the small volume and higher than average number densities. Great.
So here's the next question is from Brad Holden, and he said he may have missed this, but how do you map to the DM mass from the observations?
The mass from observations?
Yeah, the DM mass.
We got the dynamical masses independently of this work. So we found these structures with all of our spectroscopy, and we have complete dynamical information of the galaxies in these clusters. Then we measured the virial masses of those clusters. That's totally independent of this work. Then we use those to fit for our masses for everything we found here.
Great. So I'm just going to say thank you to all 6 of our speakers for this session. We're going to wrap it up.